Okay. So, what we have covered thus far is we talked about started with instrumentation, and one of the major component in the instrumentation of an ultrasound system is your transducer, which acts, as we saw, it acts as both a source, right. You could generate pressure waves as well as it will receive the pressure waves. So, on one side you can supply electrical quantity, it creates a pressure wave, and when on the reception we talked about how we will be using it as a pulse echo mode, that is what is predominantly used for medical imaging applications. So, when you have the pulse that go in, it bounces back. We saw about all the properties about the reflectivity, right, impedance mismatch. So, a portion of the signal or the echo of the signal that you sent comes back, and the same transducer, the crystal, the piezoelectric crystal, now when it is hit with a pressure wave, it gives you a voltage waveform, and that voltage waveform is taken and processed further, and you get all the image display, signal processing, put them together, organize in an image and display. So, what we need to focus, like the style that we have adopted, we did instrumentation and then we go into imaging, but right, the imaging equation or the image formation. But I told you slightly I have switched the style here, because the last part of the imaging equation, right, that we typically cover in physics, I did not cover. I said we will cover the transducer or start with the instrumentation and then bring in that equations. Okay. And so, now we are at a stage where we understand that we can use a transducer and we could give harmonic excitation, and that could give you a pressure wave. So, the challenge that we are now going to address is, what is the shape of this pulse, right, what is the shape of this waveform. So, I have a transducer, I excite a transducer, and the frequency is dependent on the thickness, that is what we saw. The thickness of the crystal determines the resonant frequency, but then we also want to know why there are different size and shape of transducer, right. So, that means what we need to understand now is, when you have a transducer, when you have a transducer of a certain size and shape, when you excite it, where all does the pressure go in the field, how is the pressure distributed in the field, or how is that wave that is propagating, for which we got the wave equation, right. Is it just going ideally just within that region, or is the pressure wave having any because it is diverging, right, is it having any weird locations where the intensity is high or low or what. So, what we call as beam pattern, that is what we want to study. So, in that context I had this displayed earlier. As you will notice, why this was displayed is, if you have a transducer, inherently it is going to diverge, right, but then it is going to retain. So, if you have a size of a transducer, say for example, this is the transducer face, right, my palm. So, it is going to get excited, it is going to oscillate back and forth, and because of that, on one side of the, so if this is the back end where you have the electrical circuit, this is the front end that is going to send it to the tissue. I excite this crystal, it is going to be oscillating, this is in a thickness mode that we call, it is going to oscillate in the thickness direction, because we are interested in compressional waves. You do this, now the question is, if you do this inside the medium, is it just going like the same way, right. Unfortunately, it is not that straightforward, it is going to start to diverge as you go, right, not just diverge, behavior of points near the transducer is going to be different. So, here is an example of the pattern that you would see. So, you could see locations where there are high pressure, locations where there are low pressure, right, and even along the center line, along the center you have high low fluctuations. Of course, after some distance it is little smoother. So, this is along the direction of propagation, this is across. So, when we do imaging, if you are just doing one dimension, this is okay, we know depth, thickness, crystal, lambda determines your axial resolution, okay. But then the challenge in imaging is you have the other dimension. So, how does this wave spread in the, at least the imaging plane, perpendicular to the depth axis. That is an important concept. So, that is what we will focus. I advise you please take a paper, pen, pencil, whatever you are comfortable, start to write the equations as we go along. Next 7 or 8 slides is just going to be brute force equations. So, my job is to kind of make you feel the physical meaning of how these equations come up, but otherwise it is going to be heavy duty with respect to number of variables. You will have 4 integrals with so many terms. So, please make sure that you have a pencil, paper, pen, start to write out. You start to write out and then listen to this commentary and then go read about it and then think about it. Only then I think you will be able to appreciate the content that we are going to do. So, with that heavy dose of caution, let us jump into the subject, which we call as diffraction formulation. So, to just give you a feel, right, before we go in your optics you would have done this Young's double slit experiment and stuff, right, where you would have had, oh okay, you have one hole, how does the light come through the other direction? If you have 2 holes, you do not get two beams, you get interference, there is going to be fringe effect, right, and you change the plane, you will see what happens to the light. So, similar effect, that is for light, similar geometric effect is also applicable to sound, and that is where you call this as diffraction formulation. So, otherwise if there is no diffraction, then it is just that okay, I have this face of the crystal that is oscillating, I get the pressure wave and it is all. So, this is cylinder, this is a disc shape for example, right. If this is disc shape, if this is moving only along the disc, right, as a cylinder column, only those particles will all nicely move back and forth if everything were ideal, but that is not the case. You have edge and you have a finite size, and therefore, you are going to have some spreading and then interactions of the waves from different locations. So, we have to develop what is called as diffraction formulation. So, we will start with what we want to operate. We want to operate in pulse echo mode. So, ideally we want to use a narrow band pulse. Okay. So, how do we formulate this? So, let us write a narrow band pulse to be n of t, which is, of course, these are all, acoustic is a physical system. So, you are going to have the real part of n tilde t with a frequency term here. So, this can be thought of as a, right, you are going to write the wave because it has a frequency, right, of the crystal, resonance frequency. So, we are going to write that resonance frequency, but we are also going to write it in terms of the envelope. So, this tilde, n tilde of t is nothing but the envelope of the signal, and there is a phase of this envelope. So, essentially we are talking about a pulse echo. So, this is the pulse that you are going to send into the tissue. So, the crystal is going to oscillate, right, in this fashion. Okay. So, you have you can look at it as a carrier frequency, and then that is modulation, whichever way you look at it, right. What you have is a RF signal with the center frequency related to your resonant frequency, and then there is this envelope. So, why is it narrow band? Oh, if this envelope, right, this pulse length, remember the pulse length I asked you to kind of pay attention to when we did the axial resolution. So, we want this pulse length, right, narrow band. What do we mean by that? So, this pulse length should be large compared to the number of cycles you have here, right, compared to the time period, the lambda. Okay. So, we'll take this. So, we'll pretend going forward this is so typically what happens is we send about 3-4 cycles of this say for example a Gaussian modulated sine wave with 3 or 4 cycles is a typical pulse form that is sent in for your pulse echo imaging. Okay. So, what we will do is, let us pretend we are going to send this guy, right, and we are going to have a real part of this n of t, and your envelope is having so magnitude of this n of t. So, you are sending this signal. So, this is going to be the signal that we think we are going to hit at the face of the transducer. So, now our objective is, so you can look at it. So, if this is what is happening at the face, if the face is going to have this vibration, right, this pressure wave that is created at the face of the transducer, then what is going to happen after it leaves the transducer and goes to a medium? How is this pressure distribution going to change, or how is this pressure pulse going to propagate? So, with the time this pressure pulse, right, this is a wave that is going to go. So, at different time instances, where is the pressure distribution? How is it distributed in space? That is what we want to go after. Okay. So, what we will try to do is set up a formulation. Again, for simplicity, there is a circle here, but this can be any shape. Remember, the thickness mode we are not worried now. The thickness is going to determine your resonant frequency. That part is taken care. So, pretend you have some thickness, so there is some fundamental frequency, resonant frequency. Now, we are interested in the shape and size of this transducer crystal. Okay, we are going to now, if you use a particular shape and size and excite it with the resonant frequency f naught as a pulse that we saw, how is the pressure, what is going to be the pressure field in front of the transducer? That is what we are going to see. So, we take a shape. So, for simplicity, it is a circle here, but you notice it is essentially can be generalized to any geometry. So, pretend this is your transducer face, you have your x naught, y naught 0, right. So, this is x naught, y naught 0, this is your origin. So, this is your point in the field, right, at some x comma y comma z, and there are some respective distances, right. So, what we will do is recognize your pressure, right, pressure at x, y, z. What is that? Oh, that is this location. So, what is the pressure experienced at this location as a function of time? Well, you are sending nt, right, this is the one that you are sending. So, if that pulse, it will take some time for the pulse to come from wherever it is generated till this location. So, that is going to take time. So, when the pulse comes there, it will probably have the same shape as the pulse that you sent. Of course, you see this term right here. What does this say? Oh, there is a small difference. How is this wave generated? Oh, this is generated from a, for example, you take a point, right? You have a circular face here. So, if it had been a sphere that is going to oscillate like this, then you have spherical waves. Whereas, what is so that we call as a monopole source. Whereas, what you have here is a disc. So, in that sense, and you are trying to do it back and forth. So, it is not opening up in all the directions, right. So, it is not a spherical wave for that reason, even though if you take the center point, right, you could pretend this disc or this area is composed of collection of several points, right. Area is nothing, collection of points. So, you have multiple points, each point is going to send out a wave which is n of t of c inverse r, that is your wave that is travelling. So, if it had been a monopole source, we would have just written our circular wave equation, right, 1 by r of the, but given this situation, this is called as a dipole model. Okay. Because of that, you get z by r naught square of this guy. This is how the pressure field comes out at any location x, y, z, and this is from a point. Okay. So, that is what is experienced from a point, but then what you can, of course, these are just giving you the dimensions. Okay, r naught is square root of this guy. Clear? This much is straightforward, because we know this is the pulse and the pulse has to travel, and at some location x, y, z, the pressure experienced will be the pulse that you sent. Of course, there is a ratio here, which is because of, which is not just 1 by r naught, for example, right, it is not just 1 by the distance, as it would be for a spherical wave. So, this is going to be slightly different because of the dipole model, that is fine. So, what happens, this is at 1, right. So, what we can do is we can write for a collection. So, if you have, this is the surface of the transducer, right. If one point, because of one point at P, X, Y, Z, you are experiencing this pressure, right. We could then talk about P of X, Y, Z, T from all the points, because you are exciting the whole surface, right. So, you can, if that is done, it is a net sum from all of the S of x comma y naught is your transducer, right. So, we talked about size and shape. So, we just leaving it here as the transducer function. So, here in this case you see S of x comma y is 1, so that it is circle. So, you have the source, right, this is your source. So, what you receive here is from all the points in the source, that is what this integral is saying, very straightforward, right. So, one point contributes 1 point, wave is generated, you receive that, but in reality the whole surface is oscillating, each point there is actually creating a wave, and therefore, what you experience here at an arbitrary location is going to be sum of all the point. So, this is Huygens principle. Okay. So, we make use of Huygens principle and superposition, and we get that. So, this is fine. So, this is on the transmit part of it, right. You transmit. So, this is how the pattern, this is what is going to be experienced. What are we interested? We are interested in pulse echo. So, what is going to come back? What is going to come back? Oh, if I pretend now this point has some reflectivity, right. If I have some reflectivity here, then if, what did we see? Oh, reflection coefficient. So, you go, you send a signal I, what you get back is I naught I with a reflection coefficient, right, PR by Pi receive, right, that is your reflection coefficient. So, PR is going to be incident times reflection coefficient. What is incident? Oh, we this is the pressure that is experienced. So, what are you going to get back? It is going to be whatever is incident times the reflection coefficient. If it is going to reflect more, then you get more amplitude to come back. If it is going to reflect less, depends on the mismatch, right. That is one thing. The other thing is, oh, this is, I say there is a reflection coefficient. What is the size of the object? If I pretend this is a point object, right, that means we already talked about it in scattering. If it is a point object, if this is going to be hit with a wave, what is going to happen? Oh, it is going to radiate back or scatter back a spherical wave. So, this is going to be a point then, and therefore, you are going to get a spherical wave. What is going to be the spherical wave that is coming out? Oh, whatever was hit, that reflection coefficient time is what is coming out. When it is coming out, it is going to come out as a spherical wave. Okay. So, your PS, which is, you can think about it as scattered, right, scattered wave, what is going to come and hit a location is reflection coefficient times whatever you sent in. Okay. Reflection, of course, this is, notice here we had Z by R naught square because it was a dipole model, whereas here it is a point scatter. So, you are going to have a spherical wave, and therefore, you are just using your spherical. So, whatever is hitting P of x, right, P of x y z, this is hit that location, its reflection coefficient. So, the R into this guy is what is coming out, and it is coming out of spherical, and therefore, you have 1 by R naught dash of this guy. So, that is what is your scattered wave. Okay. So, this is from one point response. So, what do we would like to know? So, what are you going to receive? See, the point is, you have full, when you receive also, you are going to receive it all the points. When you are going to transmit, also all the points are transmitting, and therefore, not just this point. What happens if we had one another point here? Oh, that will also behave very similarly, right? The wave would have hit, come back. What if there was a point here? So, again, so we will say on receive the medium, right? Whatever you are going to get back, you are going to have a distribution of distribution of points, okay? And therefore, what we can try to do is your received signal. So, now see what we are writing. This is our received signal x, y, z of t, correct, is whatever is falling on the plate, dx naught, dy naught is your surface here. So, everything that is falling on this, when it is reflecting, what is happening? Spherical wave comes. So, this is my transducer face, a spherical wave comes, this is my spherical wave for example, right, I am keeping this as. So, when it comes, the spherical wave is travelling, when it comes and hits the crystal back, right, on the receive side, oh, it is going to now oscillate and then convert to electrical. So, this is going to oscillate, right, pressure wave. So, whatever this spherical wave that is coming out, wherever is hitting the surface of the crystal, all of the excitations in the crystal in the reverse is going to be summed, it is going to be contributed. If it is not falling on the detector, that wave just went somewhere, we do not care about it. So, the received signal is nothing but what came out, right, the spherical wave that got reflected and came out, or that R reflection coefficient went into this some constant, right, that has to do with essentially your efficiency of conversion, for example, from your electrical to pressure and pressure to electrical, all those things contribute. So, all of that is some constant k. So, you have observed that reflection coefficient also there. So, essentially what you have is your signal that came back times wherever the surface area, all of this is contributing. So, all the collections you get, and this is for one point, okay. So, now we can expand it and say, look, that is for one point, right. So, what do I do? Oh, have a collection of points, right. You could just use simple superposition theorem, just each point is contributing, maybe they are distributed differently, right. A collection of that is what you are going to see. So, you can write your R of x, y, z of t essentially as full, I mean that is why you have to be cautious, because there are so many terms here, right. This is into, this is into. So, one is the why, what we have done is we have expanded, see we had this PS, right, scattered signal, I have just expanded that scattered signal as well, okay. So, that is why you get, I told you, right, there is going to be lot of even 4 integrals here. So, you had this, right, you have this, and then the PS was scattered signal collected over Sx naught of whatever came back. So, why is this 2 integrals? A surface area is contributing, surface is a collection of points. So, dx and dy comes there. When that field pattern goes, hits, and the reflected signal comes back or the scattered signal comes back, that is again exciting the crystal. So, that is another 2 integrals for the area dx dy, right, and therefore, what you receive is what you sent and how much came back, the echo that came back, sum of all that is what is your received signal. This is fantastic, all encompassive, but it is also complicated, right. This is just brute force substituting the wave equation and to the context of some transducer generating that wave, okay. So, now what we need to do is we need to make it little more practical, right. So, we need to simplify it. So, certain approximations we will encounter now, okay. How do I describe this wave pattern, right, the beam pattern, field pattern, so that, so this is capturing everything, but then it is not easy to analyze with this equation. So, we will make some approximations so that this reduces to a form which can be better explained, better analyzed, and we will put the context that time. So, plane wave approximation. What do we say in plane wave approximation? Remember, we are looking at some plane located, so some plane at z. All we are saying is this envelope of this pulse, right, that you are sending, they are all hitting, right, all of them are arriving on the z plane simultaneously. That is what we are going to say as plane wave approximation. Why? Because once we make that approximation, this guy, this is the pulse that you are sending, right, nt of this can be approximated to your t minus 2 zc. So, what you are going, what you are coming, right. So, 2z and you change those to the phase term. So, you can approximate. So, you can make a plane wave approximation where you say basically the envelope of the pulse are all arriving in the z plane simultaneously. If that is the case, we can mathematically represent that in this form. And if you look at this, we can even reduce it little further. Why? Because you know this 2 pi f naught is there, but then we are talking about wave number. Remember, I said it will be conveniently used because you are talking about in space, you are going to field pattern is in space. So, I would rather convert this time f naught quantity to the how the wave is propagating in the medium. Therefore, wave number becomes convenient. So, we will switch instead of f naught, right, 2 pi f naught, we will switch that in terms of k. What is k? 2 pi by lambda. 2 pi distance by lambda is your k, wave number, go look for that. Okay. So, we are just conveniently writing that in terms of wave number and splitting it. So, now what we will do is, okay, so we need to substitute this back. So, next slide is also going to be, I mean, this is a big equation, we have not done much, we will just substitute this back and then start to reduce. Okay. So, what we now call as q of xyz is just that term. Okay. So, you had two integrals, two double integrals. One of the double integrals where we are making this approximation, right, we can write, so this one, right, you had two double integrals, there are 4 integrations. Rather, by doing this approximation, conveniently splitting this as r naught minus z and r naught dashed minus z, what it turns out that if you put it back here, it turns out that you can simplify this into 2 identical double integrals. The 4 integrals became 2 identical double integrals because of this manipulation. So, the 2 identical double integral will be like this: s x naught y naught z by r naught square e power j k of r naught minus z. So, you had 2 double integrals. By making this plane wave approximation, we have reduced the 4 integrals to 2 identical double integrals. Okay. So, this is one of them. Okay. So, why is this convenient? Well, at least this is only 2 integral. Okay. So, double integral I can basically q square is what I will be interested in. Okay. So, what you are getting now is your received signal. So, it is the same equation that we had in the previous slide. Now, I am going to break the 4 integrals into 2 identical double integrals called as q of x, y, z. So, other terms remain k r, right, and then n of t z and then q x square. Okay. So, this is your received signal. So, it is already complicated, mathematically it looks too many terms, but conceptually is straightforward, right. Whatever you sent, right, the whole surface area is sending, it is a collection of points. So, the net sum of that is acting here, and then there are several points. So, what is received back is in the medium wherever there is point scattering, right. So, there is a reflectivity distribution, if you will, you are collecting back whole sum of it. That is what this says. How is that distributed? Oh, you see it here from all the surface. So, this is how the shape and size of your transducer gets into the signal that you are sending and the signal that you are receiving. Okay. So, now what we will do is, okay, superposition holds good. So, we can write your R of t, right. So, this is for one we wrote, but then we will assume superposition, and therefore, whatever you are receiving at R, right, whatever you see, the R of t is from every location that, see, this is not one pressure at one location, right, the whole surface area is oscillating. So, it is creating a pressure field transmit. So, when you receive back for one point, we wrote this, whatever is reflected at that point is R of x comma y comma z. So, if you have multiple points, right, and if you pretend superposition holds, which it most of the time holds, then what you are receiving in general can written as R of t, right. So, if I have a transducer crystal, excite it and receive, I am going to get some signal, right, R of t, and that R of t, what is it capturing? It is capturing all this from the whole region in front of the transducer where all this pressure went, right, everything on the surface of the crystal is going to be summed. So, you are going to have a R that is a function of t, because the wave is travelling. So, the echo is coming. So, there is a time axis, but x, y, z is fused. So, what you are getting, you do not know where it is coming from. All you know is it is coming after certain time interval. It is coming from the whole region that got insonified in this beam pattern. Okay. So, that is what we get R of t. So, this is fine, but even this is very good at a, intuitively addressed, but then you have several different terms. So, we need to figure out, okay, if you say that R of t is this, and t, as you can notice, even though it says t axis, if you get time, what is it saying? Oh, it is going deeper in the tissue, right. What the echoes will come earlier instances if it is nearer the transducer, the echoes from the regions that are boundaries that are further down deeper will come late. So, even though we write R of t, we know that what this is saying is the echoes are coming from different locations along z direction. Okay. So, now the question is, okay, if we talk about locations at z direction, then can we make some analysis to find out how the equation can be simplified, or is it the same equation, or can we simplify the analysis of whether if z is close to the transducer, can we, what are the effects when z is far away from, or the point, right, along the z depth, if it is far away from the transducer, what is the pressure field. Okay. So, even though it is written as t, you should kind of make that one extra interpretation that R of t that you are receiving, right, you know the time axis is going to be along the direction of propagation in some sense. Okay. Fine. So, we can write your R of t in full form, because I have just substituted this small r, right. This is what you are getting. This is the fundamental signal equation for your ultrasound. Clear? So, this is not, of course, I have conveniently introduced this term which was not there earlier. What is this? Oh, e power minus mu a z is your attenuation. Of course, I have it 2 mu a. Why is this 2 mu a? Oh, the signal is going, so it is attenuating e power minus mu a z, then it is coming back again. So, when it comes back again,
it will again get attenuated by e power minus mu. It's the same material, mu A is its attenuation in that region, right. So this is a pulse echo, this is an important piece of information. The signal, right, the time and distance, you have to be always careful because the time is going to be 2 times. It has to go because the signal that you are receiving is an echo. So the signal as the pressure wave would have travelled to that location, get reflected, the echo comes back. So you have to wait for 2 times the time for the distance. So distance and time are related, like you have to do half the, you have to travel twice the distance, right, go once, come back. For if you get your echo at time equal to t, that means you have to have a factor of 2. It has travelled twice the distance in that t. Okay, so that is a catch, very important, tricky. I'll highlight that again as we go, how we use this for measurements and stuff. Okay, but that's a reason for introducing this conveniently. So there is echo is going, echo is coming. Let's also include the attenuation there. The 2 is there because it is always, echo is going to be traveling one time further, transmit, it is going there, it is getting attenuated, coming back again it is going to be attenuated, so it is 2 times attenuation. Okay, so what we will do now quickly is further approximate, understand whether we can analyze this further. So we will take this guy, this is the main guy, right, your q of xyz. This is in some sense this is also the directional function that is referred sometimes. Okay, so we will or the field pattern that you really are looking at, right. So this is determining the field pattern, the shape, right, this integral. So we will make it little straightforward to analyze this. So what we are going to do is, first is, we are always interested in something at the center of the, right, transducer, because in the end everything is falling on the surface is going to get captured. So if I have to register that, I will have to register that at x naught comma y naught comma 0, for example, right. So you are going to say that's where the transducer was located when you got this time trace of the signal, which is depth. So in some sense we are interested in the pressure that are close to the z axis. I am not really interested in something that is off the axis that much. So we can do what is called as paraxial approximation, that is your r naught is approximately equal to z. So if you look at our q, what that helps is, that probably helps only the amplitude part. The closer you are, right, z equal to r naught, if you approximate that, you can reduce the amplitude part, you do not get anything with the phase part, right. So you can write that. So first approximation you can do that. So you can bring your 1 by z out and you have this. Okay, so this looks good. Can you recognize what is your form here? Oh, I have an amplitude term, so there is this phase term. So if I have to simplify, I have to somehow simplify. If I can simplify the phase term, maybe I can simplify this. Okay, so next we talk about Fresnel approximation. So first, to kick in, we want to simplify this phase term. So we will use Fresnel approximation. What does that say? We note here r naught, right, r naught is your square root of x minus y minus y naught plus z square. So we want to simplify this. How do I simplify this? Because this is what we are going to go after, r naught minus z. How do we simplify this term? So we recognize r naught as this, and therefore we can quickly write this as, you can take the z out and you can write it as a fraction. So far is just mathematical manipulation, but the assumption comes, or the simplification comes, is, oh, we are interested in knowing whether you are close to the transducer or away from the transducer, right. We also showed at the beginning of the module, I showed you the pattern is going to be weird if you are close to the surface or away from the surface, far field and near field. So we are going to say, look, if this is the case, there is this x naught, y naught and all are going to determine, say you are talking about, so your z is the depth distance. So if you look at this, if you can have reasons to believe that you are looking at z that is far away, right. So if z is large enough, then in this I can just use, I can ignore the higher order terms and approximate using only the first two terms for this square root expression. Okay. So if you do that, your r naught becomes the square root of 1, this I am simplifying, retaining only the first two terms. So I have 1 plus 1 by 2 of this guy plus this guy. Of course, therefore you can write z plus x naught minus. So where are we going to use this? This r naught. Where are we going to use this? Or this r naught I have to substitute here. When I substitute, what do you see? Oh, there is a z here, there is a minus z here, those two will cancel. Okay. And then you will be left with only this x minus x naught by 2 or x minus x naught square by 2z and y minus y naught square by 2z. You will be left with only that. Okay. So x minus x naught the whole square by 2z, y minus y naught by whole square by 2z. If you look at this, right, I know this is only q. This q has to be substituted in your receive signal r of t, it has to go in. So first we are trying to work on this field pattern, right, or so that is determined by this q. Okay. In some sense they also plot this and they call directivity function, right, which direction it is going. But how do we simplify this further? Do you see anything here that rings a bell? Have you seen this formulation somewhere? A double integral, you have an exponential with some, of course this is just dummy variable x naught y naught. In your formulation usually you have x and y and shift will be x naught y naught, it is just a different variable. But conceptually what is this capturing? Okay. So this is your Fresnel beam pattern, we will just recognize that this is akin to your convolution, two-dimensional convolution, right. So what we have done is we are recalling this r of t same as before, only the place where we had q of x comma y comma z square, right, the q I have simplified using Fresnel. How I simplified? I have simplified by making this approximation in the expansion in the phase term. I have used only the first two terms in the binomial expansion. If I do that, I get this form. When I get this form, I recognize this is nothing but Sx comma y convolution with this two-dimensional convolution. So in some sense, instead of writing two integrals and doing 2 dx naught y naught, I have reduced this to a recognized it as a convolution operator. Okay. So this is called as your Fresnel beam pattern. This is holding good in the near field. What you have to recognize from here is, if you are close to the transducer, so this is your face of your transducer, right, this is your face of your transducer, this is your depth, right. If you are close to the transducer, right, not only do you get the effect of this guy, but you also get the effect from the neighbors, the corner points as well, right. So as you in the near field, essentially when you are close to the transducer, you are going to have contributions from all the surface along with the point which is the closest. So as you start to move, the influence of all of the others start to diminish. Okay. So Fresnel beam pattern is complicated. Fraunhofer or far field pattern, what does that mean? Same thing, we will have to make, see the phase term we made one approximation. Can we approximate or that expansion that we wrote, can we write it some other way? So we started with r naught, z plus this guy. Can we expand this, right? So this is what we had, right? We had this r naught minus z, so this went out and we were left with this term in Fresnel. So now we go back to the same square root whatever we had. We would like to expand this further. When you do that, you have x minus x naught by 2, y minus y naught by 2 and this terms. Okay, so this is another level of expansion that we have done here. Why are we doing this? Of course, if you expand this, you have to substitute back in your r naught minus z, only this z will go. So now instead of 2 terms, you are going to have 4 terms, exponential of this, exponential of this, exponential of this, exponential of this. Okay, or here you have sum of 2 terms or exponential of sum of 4 terms. Okay, so that's what will happen. So we will have exponential of 4 terms. Instead of that, we are writing it as 2 exponentials of 2 terms. Convenient split. Rest of that doesn't change. Okay, so why do we conveniently write this? Again, we are going to always look at it. How do we reduce this double integral, or at least what is the meaning of this double integral of some function that is there operated on another function, right? You see this k, so there is some wave number which can be related to also frequencies. So Fraunhofer approximation, and in the far field what we are going to do is recognize that if you are far field, what do you mean by far field?